All right, let's just jump right in. I want you to think about something for a sec. All the heat that gets wasted every single day. The heat coming off your car's engine, from these massive industrial factories, even just the heat coming off your own body right now. It all just vanishes into the air. But what if it didn't have to? What if we could actually grab that lost energy and turn it into electricity?
Right? That is the huge question we're going to tackle. Imagine a world where all that waste heat isn't waste at all, but a resource, a way to power our devices, make everything more efficient, and build a much more sustainable energy future. It sounds like something straight out of science fiction, but it's actually a lot closer than you might think. And the key to unlocking all this potential, well, it's hidden inside a really special class of materials. They're called thermoelectric materials, and they basically perform a kind of modern-day magic trick. They can turn a temperature difference directly into electrical voltage.
So how does this magic actually work? Well, it all comes down to a really fundamental principle in physics. It's called the Seebeck effect. Here's the deal. If you take one of these special materials, you heat up one side and keep the other side cool, the electrons inside start to move away from the hot side and race over to the cold side. That movement of charge creates a voltage, and voila, you've got electricity. There are no moving parts, no emissions, just pure solid-state energy conversion. Okay, so not just any old material can pull this off efficiently. Scientists are always on the hunt for the perfect candidates, which brings us to this family of materials with a fantastic name, the skutterudites. Skutterudites are just so cool. The best way to picture their structure is like a tiny, rigid crystal cage. And inside that cage, you've got these other, bigger guest atoms that are kind of trapped in there, just rattling around. And this unique atomic setup is exactly what makes them so special for what we're trying to do. And here, you can actually see that structure in action. Look at those big red atoms. That's cerium in this case. Those are our guests. Because they're not held in there super tight, they vibrate and shake, and that rattling actually messes up the flow of heat through the material, which, believe it or not, is exactly what we want. We need to keep one side hot and one side cold to maintain that all-important temperature difference. This is just a brilliant way to see how the physical shape connects to what the electrons are doing. On the left, you see the cage itself. On the right, that's a map of electron density. It basically shows how all those atoms are holding hands and sharing electrons. This whole setup is the secret sauce. It lets electricity flow through pretty easily, but it slams the brakes on heat, and that's the golden ticket for a great thermoelectronic material. Okay, so from this whole big family of materials, let's zoom in. Researchers are putting one specific member under the microscope to see just how good it can really be. And here it is. Its full name is a bit of a mouthful, cerium platinum germanide. We'll just call it by its formula, CePt₄Ge₁₂. It's what's known as a filled skutterudite, and that filled part just means it has those guest atoms, the cerium, doing their rattling thing inside the cage. So why focus on this one in particular? Well, for a few key reasons. First up, it conducts electricity kind of like a metal. Its electronic structure is also super complex, which is actually a good thing. It gives scientists a bunch of different dials they can turn to tweak its properties. And maybe most importantly, it seems to really shine at high temperatures. That makes it a perfect fit for grabbing waste heat from places like power plants or a car's exhaust.
Now here's the thing. You might be picturing scientists in a lab with bubbling beakers. But a lot of this groundbreaking work now happens inside a computer. Why? Because it's way, way faster and cheaper than trying to physically make and test thousands of different material recipes.
The tool they use is incredibly powerful. It's called density functional theory, or DFT for short. Honestly, the easiest way to think about it is like a super advanced flight simulator, but for materials. It uses the basic rules of quantum mechanics to predict exactly how a material will behave. Its structure, how it conducts electricity, everything, before anyone even tries to build it in the real world. And the whole process is really methodical. First, the researchers pick their software. In this study, it was one called Y2K, and they build a digital model of that CePt₄Ge₁₂ atom structure. Then, they run the DFT calculations to figure out its basic electronic properties. From there, they use other physics models, like Boltzmann transport theory, to predict how it will actually perform as a thermoelectric. It's like a complete digital pipeline, taking you from fundamental physics all the way to a practical prediction. All right, so after all that number crunching in the virtual lab, what's the final verdict? Did this material live up to the hype? But before we get to the results, how do you even grade one of these materials? I mean, is there a single score that just tells you this one's an A+ and this one's a C-?
Turns out, yes, there is. It's called the figure of merit, or just ZT. And the report card analogy is perfect. It's a single, simple number that boils down all the important stuff into one score for how efficient it is at converting energy. And it's easy. The higher the ZT, the better the material. Simple as that.
So what's the recipe for a high ZT score? Well, you need a perfect storm of three things. You want a high Seebeck coefficient, that means you get a lot of voltage for your heat. You need high electrical conductivity, so the electricity you generate can actually get out easily. And here's the really tricky part, you need low thermal conductivity. You've got to keep the hot side hot and the cold side cold. And the big challenge in this whole field is that materials that are great at conducting electricity are almost always great at conducting heat too. So finding something that can do one but not the other, that's the holy grail.
So what did they find for our material, CePt₄Ge₁₂? The results were really interesting. The simulation showed it has a really strong Seebeck coefficient, which is great news. But the most important discovery was how sensitive that value is. By making tiny little changes to the material's chemical makeup, a process called doping, which is kind of like adding a pinch of a special spice to a recipe, you can tune its performance in a huge way.
And that brings us to the headline number of peak ZT score of 0.26. Now I know, 0.26 might not sound like a massive number on its own, but here's the kicker. It achieved that score at a super high temperature, 1000 Kelvin. We're talking over 700 degrees Celsius, and that's exactly the range you find in industrial waste heat, which just confirms this thing has serious potential. Okay, so let's zoom back out. We've gone from this huge idea of capturing waste heat all the way down to the atomic level and a single number. But what does it all really mean?
It really boils down to this. First, this specific material, CePt₄Ge₁₂, looks like a really promising player for turning high-temperature waste heat into usable power. Second, we now know its performance isn't set in stone. It can be fine-tuned, which gives engineers a clear target to shoot for. But bigger than that, this whole study gives us a blueprint, a roadmap for using these computational tools to discover and optimize even better materials down the line. Every study like this is another small but crucial step toward a future with a whole lot less wasted energy.
And that really leaves us with one last kind of cool thought to chew on. As these materials get better and better, the places we can use them might get a lot smaller and a lot more personal. So, think about it. Could the very device you're watching this on right now, or maybe the smartwatch on your wrist, could it one day be powered by nothing more than the heat coming off your own skin? The science we just looked at suggests that future might not be science fiction for much longer.